Okay, so we're finishing up the chapter on continuity today, and the first thing we're going to talk about are discontinuities. Discontinuities, and discontinuities for functions, for real value functions. So we're discontinuities on R1. Okay. So the first thing we're going to do is talk about something that you saw in calculus, which is left-handed limits and right-handed limits. Right, if a function, if you have a point and you're approaching this point from the left, and the function has a limit from the left-hand side, we talk about a left-handed limit. If a function has a limit from the right-hand side, you can talk about a right-handed limit. So we're just going to describe that using the vocabulary that we have now. Okay. Okay. So so here's the definition. We have some function going from an open interval AB into R1. So here's some interval. Here's some interval AB, and then there's a point X inside AB. Okay, and so here's the definition, right? If there exists a point Q in R, so that's going to be our limit value. If there exists a point Q in R, such that, well, maybe you guys can define it. Okay, what do you think? Then we blah blah blah. Then we say that the limit of f of x, the limit of f of say t, as t approaches x from the left-hand side equals q. Right? What should be the definition of the left-handed limit as t approaches x being q, using our epsilons and deltas? See, take a minute and see if you can write something down that shows you know what's going on here. Okay, talk to a neighbor. Talk to a neighbor. Somebody nearby.
It's just using the delta.
Okay, so we know
Intersect.
the entire neighborhood.
Intersection, so it's like we just kind of
And
exclude everything about
seems like
the right-hand side. I'm not sure.
we are discontinuous.
In the book, that was, that's the
Exactly.
definition, it
So-
just helps me. Yeah,
I
no,
think,
I don't,
um,
the definition in the book is like the sequences. Right, that didn't make sense.
Okay. Anybody want to tell me what we should write here? How should we describe the limit as t approaches x from the left-hand side being q? How should we describe that using epsilons and deltas? And go ahead.
I have a very tentative.
That's all right. That's good.
Answer, which
Yeah.
is just like kind of basing it on the definition of a limit.
Yeah.
Intersect with AX.
Intersect. Yeah. That's
So
that's.
like cutting out the right side?
Yes, that will do, right? So you're saying, well, look, if we're talking about just the full-blown limit, right? If we're talking about the full-blown limit, then Q should have the property that, given any epsilon greater than 0, there exists a delta greater than 0 such that, F maps the delta neighborhood, the punctured neighborhood of X into the epsilon neighborhood of Q, right? That's the full-blown limit definition. Or if you like, you could write it like there exists a delta such that if X is if the distance of X, if the distance of T from if the distance from T from X is smaller than delta and greater than 0, then the distance of f of T from Q should be smaller than epsilon. Right? Right. So that's the original limit definition, right? But we only want to talk about what happens on the left-hand side, right? So rather than saying we want the full-blown, right? We want the full-blown punctured neighborhood, we're just going to take the left side of that neighborhood, right? We're just going to take the left side of that neighborhood. So just say like such that x minus delta comma x gets mapped into there, right? So this is just the left half, right? The left half of the punctured neighborhood, right? You could call it a left-handed neighborhood, but nobody does. Okay, makes sense, right? I hope that makes sense to you. That's how we're going to define the limit existing from the left. And Rudin uses this notation. He says fx minus equals q. Okay, so that's what he means. That as you approach x from the left-hand side, a limit exists and equals q. Okay, I think this is probably more natural, easier to understand. Okay, and similarly from the right-hand side, right? If we're going from the right-hand side, then we're going to take the right half of that neighborhood. It will just be x comma x plus delta, right? So given the picture as usual, for the left-hand side, given any epsilon, right? Given any epsilon, you can find a left-handed neighborhood. You can find a left-handed neighborhood in which all these points get mapped into that epsilon neighborhood, right? No matter what epsilon neighborhood you take, there's a delta here, a left-handed delta neighborhood that gets mapped inside it. Okay, right? I can take a tiny one, and I can still find a delta neighborhood that gets mapped inside there. Okay, right? So that's left-handed limits, left-handed and right-handed limits. Okay. So here's another definition. If f is discontinuous at a point x, but the left and right limits exist, so then we say f has a simple discontinuity. At x. Okay, a simple discontinuity. So that means that it's not so bad, right? Your function, you have this point, and there's a discontinuity there, but a limit from the left exists, and a limit from the right exists. Okay, so maybe you have something like I don't know, maybe something like this, right? you get some value there, but the left limit doesn't equal to the right limit. Or you could have something like this, right? This would also be a simple discontinuity, right? It's a discontinuity. The left and right limits exist and are equal to each other in this case. Okay. The Rudin also calls these discontinuities of the first kind. And anything else is called of the second kind. So a non-simple discontinuity. So for example, if you look at the function f of x being, say, 1 if x is rational, and 0 if x is irrational, right? Then that function is very, very discontinuous. All of its it's discontinuous everywhere, and all of its discontinuities are of the second kind, right? No limits exist for this function. Right, because you see that at every rational number it takes the value 1, at every irrational number it takes the value 0. Right, so it just jumps back and forth wildly. Okay. Okay, so pretty simple. Yeah, most of the stuff we're doing today is I think not that bad. At least I hope so. Okay, so we're going to talk about monotonic functions and discontinuities. And we'll talk about monotonically increasing functions. Monotonically decreasing functions, of course, would do the same. Will have similar results. So you have some function like this. We call f monotonically increasing if something happens. Anybody, you know what it looks like, right? It's a function that oops, that's not what it looks like. Right, a function that is just increasing, right? It could be flat. That flatness is okay, but it never is allowed to drop. How do we describe this mathematically? How do we describe this mathematically? Well, we say if whenever you have 2 points and one is less than the other, you have f of x is less than or equal to f of y, right? So whenever you have 2 points, the one on the right must be, the value of the one on the right must be greater than or equal to the one on the left. So that's monotonically increasing, and of course monotonically decreasing is defined in an analogous way. So, okay, so Rudin gives this theorem that says something about monotonically increasing functions. So if f, oops, I think it's on AB, sorry. You have some function on an interval AB. If this function is monotonically increasing, then two things happen. One, for all x in AB, the limit from the left and the limit from the right exist. Okay. So what that tells you is that if your function is monotonic, then you only have simple discontinuities. Right? That's just exactly what it says. Okay. And then the second thing is that if you have these 2 points, x and y, and where one is less than the other, then the limit from the right of x is less than or equal to the limit from the left of y. Okay, so you got these 2 points, right? Here's A, B. You got 2 points in your interval. The limit from the right has to be smaller than the limit from the left of this. The limit from the right of this guy must be smaller than the limit from the left of this guy. Okay, so that's something that you would expect. We'll use this in the next theorem. That's why it's being introduced here. Okay, so let's prove the first one. Okay, so here's A, here's B, and we have some point x. Right? So let's call the variable t. Right, and we want to show that that there's some point that satisfies the epsilon delta condition, right? The epsilon left-handed neighborhood condition, right? So how are we going to get that point? How are we going to get that point? Anybody know how we're going to? We want to show that there's that as you approach x from the left-hand side, that the values approach some limit, right? How do we find that thing that they approach? Anybody? There's sort of an obvious, a natural tool to use, a natural idea to use at this point. Anybody have an idea? What happens if we look at all the values to the left of here? Okay, all the values to the left of x. Okay. Yes.
Is this the least upper bound property?
We're going to use the least upper bound property. Yeah. So right, because they're increasing, right? There's a set, and you've got these increasing values, and it's bounded above. It's bounded above by, say, the value at x, right? So, like, here's some value at x itself, right? Here's f of x, right? Now look at all the values that occur between a and x, right? You've got some values, blah blah blah. Whatever it is, it's a set that's bounded above, right? So it has a least upper bound. That least upper bound is going to be the limit from the left-hand side. Okay, right? So kind of a natural thing to do. So what you do is you say, let A denote the supremum of all the values where t ranges between a and x. Right? So just take all the values as t ranges between a and x. We claim that the limit from the left-hand side of x is going to be a. Okay. So, right. So here is a right here. Okay. And so what do we want to show? We want to show that given any epsilon, right? Given any epsilon neighborhood here, we can find a left-handed delta neighborhood of x that gets mapped inside there. Okay. So let's fix some epsilon greater than 0, right? Pick some epsilon, right? We want to show that there's an interval x minus delta x such that if t is inside there, then f of t is bigger than a minus epsilon. Right? We don't have to worry about it. We don't, yeah, so we know f of x is going to be smaller than a, right? We know this is going to be true, right? Because a is the supremum of those values, so we don't have to worry about that part. All we have to show is that f of x is bigger than a minus delta, a minus epsilon. Okay, so how do we find that delta? So somebody gives us an epsilon, right? Somebody gives us an epsilon and says, can you find a delta where everybody gets mapped inside here? Right? You can say, well, just look at the picture, sort of, right? Look at the picture. You know that at some point you have to cross that line, right? Right. So we know there must be some x naught. There must be some x naught smaller than x, where f of x naught is bigger than a minus epsilon. Right? There must be some point where you cross the line. Right? If there isn't any point where you cross the line, then that thing was not the supremum. Right? If you never cross this a minus epsilon line, then this a was not the supremum. Right? So there must be some point, right? Some point to the left of x where you cross the line. Right? And you also know that after that point, you stay above the line, right? Because it's an increasing function. Right? For all t in, right, so, right, else a was not the supremum. Right, so further, for any t bigger than, for any t in x naught comma x, right? For any t in x naught comma x, we know that f of t must be bigger than or equal to f of x naught, which is bigger than a. Right? Right. We find some point where you cross the line. Call that thing x naught. Right? Any point to the right of there, any point in this left-handed neighborhood of x is going to be have a value bigger than a minus epsilon because it's increasing, right? Since f is increasing, right? And so we were done, right? We found the left-handed neighborhood in which all values get mapped into the epsilon neighborhood. Okay, it's maybe not that interesting. Okay, maybe that's not that impressive, I guess. Okay. 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 So yeah. So what do you see? That for monotonic functions, all left-handed limits exist and all right-hand limits exist, and so you only have simple discontinuities. So similarly for the right-handed limits. Okay. This proof of part 2 is equally straightforward, right? So here's A and here's B, and you have some X and you have some Y. Okay. So okay. So the thing to notice is that okay. So we want to show that f's limit from the right-hand side is smaller than y's limit from the left-hand side. Okay. So let's think about what these things are, right? F's limit from the right-hand side is the infimum of all values where t ranges from x to b, right? Because that's how you would get it. You look at all these values, you take the infimum, right? Y's limit from the left-hand side, what's that going to be? Well, that's the supremum of f of t, where t ranges from a to y, right? Okay. But the infimum over this thing here is the same thing as the infimum of f of t as t ranges from x to y. Right? So I'm saying that instead of taking the infimum over this thing, so our function is decreasing. Right? If we're looking at the infimum over this thing, it's the same thing as the infimum over this thing, right? Because our function is decreasing as we approach from the right-hand side, right? So we don't need to consider this part, right? This part is bigger than this part, right? So the infimum over this thing is the same thing as the infimum over this thing. Okay. Who sees how we'll finish it? Who can finish it for me? Go ahead.
I think we could do the same thing for the supremum, so that it's over x is less than or equal to t is less than or equal to y.
Yep.
And then it follows that the infimum on that interval is less than the supremum.
Exactly. Right. So this thing equals the infimum over here. This thing is going to be equal to the supremum over here. Well, the supremum over here is definitely bigger than the infimum over here. So that's the end. So I'm not gonna write it out. Okay. Simple. Okay. Okay. So now we get to the theorem that's at least somewhat interesting. So if f is monotonic on some interval, then the set of discontinuities is at most countable. Okay. So whenever you have a monotonic function, you know that it can't have uncountable discontinuities. Or conversely, if you have uncountably many discontinuities, you know your function's not monotonic, right? So like, this function, the 1,0 function had uncountably many discontinuities. We know that it couldn't have been monotonic. Okay, so. Okay, so here's the proof. You say, well, let x be a discontinuity of f. Okay. By what we just said, we know that the limit from the left and the limit from the right exist, right? Because it's monotonic. And we also know that actually the one on the right, from the right, has to be strictly bigger than the one on the left, right? It can't even be equal, because if it were equal, then you'd have a continuity there, right? Because they would be equal, and the value at x would have to be that value. So you'd have continuity. Okay, so so we know that they exist, and that this guy is strictly smaller than the other. Okay. Okay. So now, by the Archimedean principle, we know there exists a rational number, some rational number such that R lies between these two numbers. Okay. So what we do is basically whenever we have a point, right? We know that the limit from the left is going to exist, the limit from the right is going to exist, right? And so we choose a rational number inside there, and we sort of tag it, we associate it with that rational number. Okay. Okay. Now suppose we have another discontinuity somewhere, right? Suppose we have another discontinuity. Well, we know we're going to have another tag here, R2, right, or R prime. How do we know that we don't tag it with the same number? How do we know that we don't tag it with the same number? Yes, exactly, right? Because you know that the limit from the left-hand side of this guy is bigger than or equal to the limit from the right-hand side of this guy, right? So this thing here is bigger than or equal to this height here, right? Is bigger than or equal to that, right? So when you know that the tags have to lie in disjoint ranges. Okay. Okay. So so since if y is another discontinuity, then we know that the limit from the left-hand side of y is bigger than or equal to the limit from the right-hand side of x, right? So so let me call this R sub x, R sub x, R sub y, right? So R sub y lies in this interval, right? But this is bigger than or equal to f plus x, right? Sorry, this should be less than. Right. So R sub x is strictly less than R sub y. Right. They can't be equal to each other, right? Because of the inequality here and here. Or just here. Right. So what does that give you? In this way, we obtain a one-to-one correspondence. Right, R going from between the set of discontinuities of F and a subset of Q. Right, we get this map R that takes discontinuities and maps them to rational numbers in a one-to-one way, right? And so we've got a one-to-one correspondence between some subset of Q. The subset of Q is at most countable, right? Which is at most countable. Okay, clear? Questions? Yeah.
I'm just kind of confused how we can just decide. I mean, I guess we're not just deciding there's one-to-one correspondence, but just how we get there just by picking rational numbers.
Well, so we're creating a map, right? So basically this line here is to create a map between the set of discontinuities and the rational numbers, right? So given a discontinuity, we look at the left and right. We look at the left and right limits and choose a rational number between them. Okay, and that is our map. X goes to R sub x. Okay, so we do that for every discontinuity. We have some other discontinuity. We're going to get R sub y there.
But I'm confused how that's mapping, like, that's not the actual discontinuity. The discontinuity is at f of x. So how can we just pick an arbitrary number between those and say that that relates the discontinuity to R?
I guess
There's an order there.
What's that?
Because like when you choose the two rationals,
Mhm.
there is an order. There will be an order, like a less than order.
Mhm.
So if you have a set of them, there will be a set of orders, right? So left one will be always lesser than the right one. So you can map it to the natural numbers, so equal 0. Because natural numbers like 0, 1, 2, 3 go.
Mhm.
Right?
Yeah.
Just
I'm not.
ask that.
Yeah, I'm not sure if that. Does that answer your question? Or?
No.
Right? Yeah. So I think I'm not quite sure what troubles you. Okay. Start off with a discontinuity, right? The discontinuity is called x, right? There's a discontinuity at this point. We associate with x some rational number we tag it. We say we tag it. Suppose this is like this is like 1 and this is 2. Say. So we say we're going to tag x with the number 3/2, a rational number between the left and right limits of x. Right? So here's the process. You start off with x. You look at the interval. You look at this interval, and then you choose a rational number in that interval. Call it R of x. Okay. So this is a function. I guess maybe you're troubled by the choose part.
Yeah, kind of. It just seems sort of random.
Yeah, so it is
And
arbitrary. It is arbitrary.
Yeah.
So, but yeah. So what you're noticing is something called the axiom of choice, actually. That if you have a collection of sets, it's and this is actually an axiom that you have to put at the base of your mathematics. That if you have a collection of sets, it's possible to create a function that chooses an element from each set. Okay, so your skepticism was shared by a lot of people, actually, and so in the 60s or so, there was a lot of argument over whether or not you should include the axiom of choice in mathematics as one of the fundamental axioms of mathematics or not. In fact, if you go on and take a course in measure theory, you'll find that so measure theory is sort of like a way of one thing you do in measure theory is to get the measure or like the length of a set. Okay, if you allow the axiom of choice, then it's possible to create sets that cannot be measured. So I think it's the case that like that's the only way that these things exist. So if you allow it, then you're allowing some sort of abominations into mathematics. And so there was a lot of argument over whether this was allowable or not. But this is basically what we're using here is basically the axiom of choice. That given some interval, we're allowed to say create a function that chooses a point from that interval. And by Archimedean principle, we can ensure that it's a rational point. Yeah, yeah. But your hesitance is not unique. Yeah. Yeah, when I had a professor in college who I think had been, he had been a graduate student at Princeton, and there were pictures of the graduate students on the walls, and so we found this old picture of him like wearing a T-shirt saying "Support the axiom of choice." Right. That was yeah. When he entered the graduate program there, that's what he wore to the graduate student picture. Support the axiom of choice. Yeah. Yeah. Along the same lines, some years ago when I was at a math thing in Utah, it happened to occur at the same time as the 4th of July, and we carried signs saying, down with triangle inequality, right? Support triangle equality. Yeah. Okay. Okay, last thing in this chapter is limits and infinity. So we've only been talking about limits at finite points, right? We also want to be able to talk about limits as a function goes off to infinity, right? So there's some value. There's some value q, and we would like to say, that for this function, the limit of f of x as x approaches infinity is q. Right. How do you think we should define this? Definition, you have some function, so you have some function, suppose it's on the whole real line, say, just for convenience. We say that the limit of f of x is q as x approaches infinity if, again, we're going to do some sort of delta, like epsilon delta definition. Anybody see how we might do it? So if given any epsilon, somebody gives you an epsilon, you should be able to find something where the epsilon condition is satisfied. What should be a neighborhood of infinity? And go ahead.
I think the book said it was like the open interval between some number and infinity.
Yeah, so for all epsilon, there exists some left-handed point, there exists some n, say, such that f of the interval n infinity is contained inside of the epsilon neighborhood of f of x. Okay. So in other words, there's going to be some point. And past which all the values are inside of your epsilon neighborhood, right? So this thing here is your neighborhood of infinity, right? Your delta neighborhood. But there's no delta here because delta is, you think of as a radius. This radius is infinitely long. So I'm not going to call it a delta neighborhood. I'm going to call it an n neighborhood of infinity. Right? It's some sort of left-handed neighborhood of infinity. Right? Infinity is over there, and we've got things to the left of it like that. Okay. Another way of saying it is that there exists an n such that for all such that if x is bigger than n, then f of x, the distance of f of x from q is smaller than epsilon. Right? F of x minus q is smaller than epsilon in absolute value. Okay, so this is the same sort of thing, and you can see that the theorems that we had for finite limits, if, for example, showing the uniqueness of this sort of limit is going to do the same. It'll be basically identical proof. Like if we wanted to show uniqueness, we'd say, well, suppose that there are two limits, q and q prime, right? If both of these guys are limits, then take epsilon to be smaller than half the distance, right? Take epsilon to be smaller than half the distance between q and q prime. So if the limit is q, we know that there's some point past which everybody's inside those two bars. If the limit is q prime, we know that there's a point past which everybody's inside this thing. But then if you're past both of them, the point should lie in both neighborhoods simultaneously, but they don't intersect. Right? It's the same proof as in the finite case. Okay. So so the proof, this sort of theorem, or theorems about the limit of f plus x as x goes to infinity being equal to the limit of one plus the limit of the other, the limit of g, right? This sort of theorem also goes there. Okay. We have a minute. Let me just mention that in complex analysis, there's actually a very concrete notion of infinity. Infinity, what you do is you take the complex plane and you identify it with a sphere. So you take a sphere and you put it up, you let it sit at the origin, and you do something called stereographic projection. So here's the North Pole, and what you do is you take every point on the sphere, you draw a line, you draw a ray going from the North Pole to that point. So you've got the sphere sitting up here. The ray is going to pass through this, is going to intersect the sphere at some point, right? And that gives you the map. So you say, we're going to identify every point on the plane with its corresponding point on the sphere, which is called the Riemann sphere. Okay, this process is called stereographic projection. And you see it gives a one-to-one map between the plane and the sphere, excluding the North Pole itself, right? There is no point on the plane that gets mapped to the North Pole, right? But you notice that as you get farther and farther out, right, the projections get higher and higher up, right? And so it makes sense to this set here is non-compact, but you can add this point here and compactify it, and call that thing infinity, right? It makes sense to call this infinity in the sense that the farther and farther out you get, the closer you get to this point on this North Pole. So that's infinity in complex analysis. Okay, that's it. We'll see you guys next time.